We've seen that some substituents are activators, orthopara activators, and orthopara deactivators. Now we're going to look at the meta deactivators. All of the electron withdrawing groups, the halogens, the pi systems, with an electronegative atom that is second from the ring, or a substituent that has a positive charge, all of those are going to be electron withdrawing groups. The halogens are they're orthopara directors, but all of the pi systems are going to be meta directors. The amine salts actually won't even undergo any electrophilic reaction, so they're such a deactivator that the deactivators pull, the meta deactivators pull electrons from the pi system through resonance. Here is a meta deactivator. Notice there is an electronegative atom on a pi system, one away from the ring. This actually causes electrons to be pulled onto the oxygen because it's very electronegative through the pi system. So what that ends up doing is putting a positive charge here in the ortho position, and it will be here in the para position and in this ortho position. The positive charge in the ring causes deactivation. The positive charge in those locations cause those positions to be very deactivated to addition. The only positions that don't have positive charge remaining in them, right here and right here, the meta positions, those actually are not deactivated there, and electrophilic addition can go there. Because the positive charge is residing primarily in the ortho and para position, when electron withdrawing group like this is present, you get meta direction. So these are the meta directing deactivators. Notice you have a carbon that has a double bond to an oxygen, a carbon with a triple bond to a nitrogen with a double bond to an oxygen, a sulfur with, this is actually sometimes drawn with two double bonds to it, but a sulfur with a double bond to an oxygen. All of these are deactivators and meta-directing, and they all prevent Friedel-Crafts alkylation and acylation because in the Friedel-Crafts reaction, those electrophiles are weak. So this deactivation actually puts an end to that reaction when it's on a ring. These substituents put an end to the Friedel-Crafts alkylation and acylation when they're on the benzene ring. So this is a summary of all the substituents and how they will direct electrophilic addition. Notice these all have an oxygen or a nitrogen directly attached to the ring. They are activators. This has a carbon directly attached to the ring. A carbon with a double bond directly attached to the ring. So as long as you don't have a double bond to an oxygen like over here, these are going to be activating if there's a carbon. So all of these are activating and they are orthopara directors. Benzene, of course, is our like zero place. It's neither activated or deactivated. Then we have the halogens, and these all are deactivators, but they're orthopara deactivators. So here, these are orthopara activators, orthopara deactivators. Why is fluorine more more activating than iodine? Iodine is more deactivating because fluorine's orbitals, even though fluorine is very electronegative, fluorine's orbitals overlap well with the pi system and can donate electrons that way. Iodine's so big, its pi orbitals don't overlap very well. And the electronegativity of the iodine actually pulls electrons to it. All of these are deactivators that are metadirecting. What do they have in common? These all have an electronegative atom on the end of a pi bond. And those end up being metadirected and deactivating, and they do not allow Friedel-Crafts acylation or alkylation to occur. Here we have a nitrogen with 3 alkyl groups on it and a positive charge. Because this bond is to the benzene ring, there is a positive charge on this. This is deactivating, so deactivating it will prevent electrophilic addition from occurring. Notice it says Friedel-Crafts alkylation will not occur with the amine. Why? It is because when you put an alkylating agent in there for a Friedel-Crafts, it reacts and becomes this. And so then Friedel-Crafts alkylation will not occur. Here are some examples. This is benzoic acid. It's got a double bond to an oxygen here. So it is a metadirecting deactivator. The reaction here, the chlorine substitution reaction, goes slower than the benzene ring, the naked benzene ring, and the chlorine is directed to the meta position. Here we have an alkyl group. Alkyl groups are orthopara activators, so this goes faster than a naked benzene ring. And what do we get? A chlorine in either the ortho position or the para position. Here we have a carbon that has a double bond to another carbon. So this is an orthopara activator, and it goes faster than plain benzene. What do we have happen? The nitration occurs in the ortho or the para position. But this compound has a carbon with a double bond to an oxygen, so it's a deactivator. This reaction goes slower than plain benzene, and it directs substitution into the meta positions. So what do we get? We get meta-nitro acetophenone. Okay, where would sulfonation occur in bromobenzene? Because bromobenzene is an orthopara director, and remember it's deactivating, but the reaction would go ahead and sulfonation would occur in both the ortho position and in the para position. Where would iodination occur on a cyanobenzene compound? Well, the cyano group is a meta deactivator, and iodination would occur in the meta position. If there's more than one substituent, what you have to do is take each substituent and figure out where it points to and which one will have the greatest effect. Well, if I look at this one, you can see that the methyl and the methyl are identical. They're orthopara directors. Where are the ortho positions? Here, here, and here. Where are the para positions? Here and here. Those two positions are identical. This ortho position is not going to go ahead because you have too much steric hindrance from these groups. So what you will get is iodination in the ortho position here. Go ahead and try to do this compound. Well, if I look at this compound, you can see that the methyl group is an orthopara director, and only the ortho positions are open. The nitrile group is a meta director. So where does bromination occur? Bromination will occur in these two positions. So what forms? This compound. Go ahead and try to identify where each of these would be brominated when treated with bromine and iron 3 bromide. Well, if I look at this, you will see that you have a nitro group here and a methyl group here. The methyl will be an orthopara director, And if you look, the nitro group is pointing to the two positions here also, which are meta to it. So where would bromination occur? Bromination would occur here and here, although it would be more likely in the first identified position. Where would bromination occur on this molecule? Well, if I look, this is a meta director, so here and here, which is already substituted. And nitro is a meta director, so here and here, which is already substituted. So the only position which would be brominated would be right here. What about if you have amino and an ethyl group? The ethyl is an ortho para director. The amino is an ortho para director. So these three positions are all ortho and para to both of them. This is rather hindered and not going to be substituted. So where can we have substitution? We can have it here and here. If I look at this next one, where would substitution occur? Well, this next one, you can see that this ethyl group is an ortho para director. So these are the two only positions open. And the amino is an ortho para director. And again, only the ortho positions are open. The ethyl is not as strong a director as the amino group. So where would substitution most likely occur? It would most likely occur ortho to the amino group. So where would each one of these be alkylated in a Friedel-Crafts reaction of methyl chloride and aluminum chloride? Well, if I look at this, we would see that we've got an ortho para director, so being directed here and here. And we've got an ortho para director being directed here and here. The oxygen is a better ortho para director than the carbon. So where would substitution occur? In the ortho and in the para position to the hydroxyl group. What about on this ring? Where would alkylation occur? Well, if I look at this ring, you can see that this and this are both meta directors, but they're deactivators. And these things do not allow Friedel-Crafts reactions to go. So that reaction would not occur. Look at the next one. If I look at this, you can see that's an ethyl group, which is an ortho para director. That's ortho also. And this is an amino group, which is ortho para. The problem is this amino group will be alkylated by the methyl chloride. And that will put a positive charge on this because it'll make the tetraalkyl ammonium salt. That positive charge here will prevent any alkylation from occurring. So this is not going to go ahead with a Friedel-Crafts alkylation. If I look at ethyl and cyano, tell me where the reaction would occur. This one's a tough one. Ethyl is an ortho para activator and cyano is a meta deactivator. So if it was just the cyano on the ring, I would say that Friedel-Crafts alkylation would not go ahead. But this is an activator, and what you would find is this ring would very slowly undergo Friedel-Crafts alkylation because it is both activated and deactivated. Where would it alkylate? It would alkylate in the ortho